So iterative methods for solving systems of linear equations. What does this mean? Why iterative methods for solving systems of linear equations? So cost of solving a linear system with direct methods are n cubed. This is too much. If n gets large, then n cube is huge and costs become intractable. That's okay. This is fine. I just want to get to the meat of it. So this is like a graph which can show, for example, this is the iterative method. This is the blue line here represents the numerically accurate method. So which would in n steps or in n cube steps will give us no progress, and then bam, all of a sudden it's to the real value. For example, householder. You keep applying Q from the back on the left hand sides, and as soon as you applied m Qs and m cross n Qs, it's like done. But iterative methods are something like, you know, xk plus 1 is some function of xk. So it's like I keep applying, and then xk plus 2 is the same function on xk plus 1. I keep going and refining. For example, the modified Gram-Schmidt algorithm, in which what we do is take the first column, second and third and so forth, subtract the parallel component of this from the remaining, then go to the second vector, subtract the parallel component of this from the remaining, and this third, and then so forth, you know. That's just iterative methods. That's just an iterative method. The point is that iterative methods can converge faster until, you know, like residual is below machine precision. Yeah, whatever. So classical methods, example Gauss elimination, follow the pattern of taking O n steps and each step costs n square, but don't exploit properties of the matrix. Iterative methods reduce the number of steps and the cost of each step depending on properties of the problem at hand. Okay? The ideal iterative method requires O of 1 steps and O of n costs per each steps to reach machine precision. Okay, iterative methods even in the absence of, so it's like a constant, so it's like given whatever problem, an ideal iterative method would take a constant number of steps, and each step takes O of n operations, so it's overall O of n algorithm. So iterative methods, even in the absence of rounding errors, do not deliver the exact answers. Yes. So that's the thing. For example, if you had infinite precision, infinite decimals, infinite memory, if you had infinite memory, QR decomposition from householder transformer will give you exact arithmetic. However, iterative method will not give you exact, even if you had an infinite number of precision, you know. So, however, we can only be as accurate as machine precision anyway if we do calculations on a computer. Furthermore, often matrices are stemming from discretizations of PDEs, and then we need solution only up to a discretization error. Anyway, I mean, you know, like if we were in intergalactic computing facility where we had infinite memory, then maybe iterative methods are not accurate. But on this planet, I don't know what I'm saying. So yeah, here's the idea. To construct, we are going to solve linear systems, Ax equals to b, in an iterative manner. We solved Ax equals to b before as by doing LU decomposition, right? We broke A into LU. I did not make a video of it. I did not study it, to be honest. I broke A into LU from Gauss elimination, and then we computed X based on that LU decomposition, right? So now we have to do it in an iterative manner to construct a sequence x1, x2 of iterates that converge fast to the solution x, where xk plus 1 can be, the next step can be cheaply computed from x1 to xk. Example just one, that's just cheaply computed. If we can compute one iteration with cost O of n, example 1, yeah, and need a constant O of one number of steps, then we solve. So for example, if this was an ideal method, that's what this statement is trying to say, we would have a constant number of steps, O of 1, and O of n per step. Intuitively we cannot do better than that, because we need to solve for n quantities, and thus, I mean, we need to solve for n quantities, and therefore we need to touch at least, I mean, we need to touch and refine all of those quantities. So O of n is like the theoretical, intuitive, not a theoretical proof, but it's intuitively that the best we can do. Okay. So let's start by trying to write Ax equals to b as x equals to f of x, and yeah. Let's see here. So this is what we write our method as. I want to write my x equals to f of x, so that I can keep plugging in x and I get something out, and I keep plugging it in and then I get something out. So what this f of x is, x equals to f of x. Oh well, ax equals to b. How about I add subtract x? So ax plus a minus identity x plus x equals to b, right? All I did was subtract x. So x becomes identity minus a x plus b. Is that what it is written over there? Cool. Identity minus a times x plus b. Okay. So now we need to solve this by a fixed point iteration. That's it. Okay. That's fair. So that instead of picking a specific f, let's look at a prototype. Like instead of making this very claim that I only add subtract identity, I could have also subtracted something else. Let's only look at this one, where xk plus 1 is gxk plus c, right? Where g is an iteration matrix somehow related to a and c is somehow related to b. We must have an actual solution x equals to a inverse b as a fixed point of the iteration, and we need the sequence xk to converge. I mean, if I plug, what the statement says is, if I plug a inverse b in this, then it should be like a consistent, it should have RHS equal to LHS. That's what should happen. So the fixed point method xk plus 1 is gx plus c with an invertible g converges for each starting point x naught if and only if rho of g is less than 1, where rho is the maximum eigenvalue and therefore the spectral radius. Let's see the proof. For G symmetric, if G is symmetric, then I have, so yes, here's why it's depending on eigenvalues. When we were doing the SVD videos, we saw that SVD tells us about the properties of the matrix, and eigenvalues tells us about the iterative properties of the matrix. Well, here it is. The iterative properties of matrix are needed again because we keep applying G again and again. So it makes sense that it's about eigenvalues. So let's do it for G symmetric. If G is symmetric, then there is a similarity transformation. Just the eigenvalues. Well, this is just the eigenvectors, left and right eigenvectors. So eigenvalues lambda 1 to lambda n, where each lambda is less than 1. Limit this diagonal power. Okay. So this G is equals to Q transpose dq. I think this is something that's written wrong here. And I raise it to a power k. Well, just this becomes k, d to the k, and d to the k will go to 0. So this will, so limit g to the k, limit g raised to the power k will go to 0. If all of its eigenvalues in modulus are less than 1, then the kth power where k goes to infinity, this goes to 0. Limit is 0, just a 0 matrix. So let's look at this, xk plus m minus xk. This is the minus xk. So this is like going from step k to step k plus m. So like taking m steps, and what I'm seeing here is that as I'm going to take k to infinity, what I want to show is that in m steps there is no progress whatsoever. Like as k goes to infinity, you take one step, you take m steps, there is no progress to add. That means that this has converged, right? Because if in m steps there was some finite difference in xk and xk plus m, that means my method has more to do. But then because there is none, as I will show, then that's fine. So xk plus m is g xk plus m minus 1. What was the prototype? Plus c or plus b? Plus c. Plus c minus g x k minus 1 minus c. So c and c gets cancelled. The norm of this is same as the norm of this. This is g times xk plus m minus 1 minus x of k minus 1. Right? I can take the k powers out. It becomes g to the k xm minus x0. Right? Whatever this norm is this, and this is less than equal to norm of g to the k xm minus x0. Well, for the first m steps, it's going to be some finite value, let's say f for finite, and the g to the k will go to 0. So yeah, so my method will converge when my method will go to a fixed value when my g is has eigenvalues less than 1. That's fair. Where my g is the prototype matrix. So xk minus x, if x is the fixed point, is same as for any induced matrix norm, we have rho g is less than equal to the norm of g, and thus the norm of g is a sufficient criteria for convergence. So if the norm of g is less than 1, that means my method will converge, always converge. Right? Can I prove it? I think I can prove that. Xk minus x is just the same as gxk k minus 1, or gxk minus 1 plus c minus gx minus c plus c, sorry, where x equals to gx plus c, because that's the fixed point, right? That's the definition. So this just becomes g times xk minus 1 minus x. So I can take the k powers out, and this becomes x0 minus x, and x0 minus x norm is whatever, and g is whatever. Sure. So this like it goes to the finite. It not only does it converge, but it converges to the fixed point. That's also the proof. Now, how do you make this G matrix? You make this G matrix by just, I multiply. So I have AX equals to B, or so let's say B minus AX equals to 0. I multiply with Q inverse. So Q inverse times B minus AX is equals to 0. So identity minus Q inverse A X equals to Q plus Q inverse B equals. So yeah, I mean, it's just a step. It's just a step where X becomes GX plus C, where G is identity minus Q inverse A. So in fact, what I previously wrote was just adding, subtracting an identity, right? But that can be generalized to any matrix where of this form. But C is also Q inverse B, right? So a matrix, if I have an invertible matrix Q inverse, if I have an invertible matrix Q, I can write G as identity minus Q inverse A, and I can write C as Q inverse B, and this will give me a fixed point iteration. Right? Now I just, and X equals to A inverse B is a fixed point. Can we prove that? So Gx plus C is identity minus Q inverse A, X plus Q inverse B. X minus, I mean just open this bracket, X minus Q inverse AX, where Q inverse AX is equals to B. So Q inverse AX is Q inverse B, and Q inverse B, so Q inverse B is cancelled. So X is a fixed point. So for any invertible matrix Q, this is a fixed point iteration, right? So Q needs to be invertible, and Q is I minus QA, right? So what can be the extreme cases? We first saw already Q. When trying to motivate the idea of this, we substituted Q as identity. So by choosing Q as identity, we can always get that's the most basic one. But if I choose Q as A, then our iteration is I minus Q inverse A, Q inverse B, where Q is A inverse B. So this I minus A inverse A, it gets cancelled, and A inverse B is X. So xk plus 1 is X. So just first step and we are done. And that makes sense, right? Because I already had A inverse. What else do I need? I already had my A inverse. I don't need anything else. I just need to multiply it with B and I'm done. So thus, if we know the solution in form of having the inverse A inverse, then no further work is needed here because we already did all the work when finding A inverse. I mean, somebody gave A inverse to us, that's it, we are done. Another extreme case is studying Q is equals to I, which we already did. This leads to the Richardson method. We have invested we did zero work in trying to find Q inverse, and thus Q inverse, and so we can expect that Q equals to I will require high cost in terms of number of iterations to converge in general, if it converges at all. So when does the Richardson method converge? The Richardson method will converge when rho of G is less than 1. All of my iterative methods will converge when rho of G is less than 1. Rho of G is rho of identity minus A. Identity minus A, the eigenvalues of identity minus A will be 1 minus the eigenvalues of A, right? That's just the eigenvalues of this. So the maximum of all of these, all of the 1 minus eigenvalues, that should be less than 1. That's needed. So the lambda max should be less than 2. So for example, eigenvalues of A can go as high as, let's say, 2. If my eigenvalues of A were the highest eigenvalue, let's say my highest eigenvalue is 5 and it goes up to minus 5. So 1 minus this becomes minus 4 and 1 minus this becomes plus 6. Okay, so this is not good. So my highest eigenvalue can be 2. Let's say if I put 2, 1 minus 2 becomes minus 1. That's good. That's like almost on the edge. And the lowest that my eigenvalue can be is it has to be 0. Because 1 minus that will be 1. Right? So all of my eigenvalues of A should be anywhere between 0 and 2. Yeah. So my lambda max of A is less than 2 and my lambda should be greater than 0. That's true too. Because if my lambda was, let's say, minus 1, 1 minus minus 1 becomes 2, so that's not good. If my lambda was, let's say, 1, so 1 minus eigenvalue 1 becomes 0, so that's good. So yeah. So between 0 and 2 should be the eigenvalues of A. In that case, my Richardson will converge. If my eigenvalues are between 0 and 2. If my eigenvalues of A are between 0 and 2, in that case I can choose my Q as identity and it will converge. So lambda max of A should be less than 2, and if A is symmetric positive definite, if A is symmetric positive definite, in that case my lambda is greater than 0, so it's okay. The Richardson method is consistent, solution is a stationary point, but it may not converge or converge really slowly. What could we do instead of the Richardson method? So what other Q can we choose? So let's think of Q as a preconditional to the Richardson method. So as close to A inverse as I can make Q inverse, that will be better for me, right? For example, if Q was A and Q inverse was A inverse, I'm done in one step. But if Q is identity, I may take a lot of steps. So let's go somewhere in the middle, in this whatever functions, whatever space I'm thinking in. So applying the Richardson, yeah. So some common choices for Q. So again, let me think. G was I minus Q inverse A. That was my G. Right? Escape I minus Q inverse A, and as close to A inverse as I can get my Q inverse, I'm better off. So one we can so if we can solve this Q thing faster, we'll be done quicker. So X is Gx plus C, where C is just Q inverse B. So I just multiply it all the way with Q. This is the same equation as that. So now the idea that we are trying to motivate is, let's say what if we chose our matrix in such a manner that A is the lower part, the diagonal part, and the upper part. So and what if we chose our Q as our D, like just the diagonal elements of this matrix. This is known as the Jacobi iteration. The Jacobi method converges for any starting point x naught to the solution of Ax equals to B if A is strictly diagonally dominant. Okay, can we prove this? So xk plus 1 is I minus, all we need to show that the G that we are constructing has a eigenvalue less than 1 or the norm is less than 1. So let's do it. The G is 1 minus D inverse A, D inverse B. Okay, I split it open. D inverse D, I cancelled. It's D inverse L plus R, that's my G. My G right now is minus B inverse L plus R, right? Let me see how much battery do I have left in my phone. Yes, okay, recording. So now I have to show that the rho of this is less than 1. Or I can just show that the infinite norm, because the norm is always greater than the eigenvalue. My infinite norm is less than infinite norm is L plus R. Yeah, this is fair. This is fine. L plus R are all the elements except the diagonal, and D inverse is just 1 upon the diagonal element. So the maximum of those is less than 1, and if it's strictly diagonal dominant, that means for all my rows, my diagonal element is more than the sum of the non-diagonal elements. So in that case, it converges if it's strictly diagonal. And this is a good choice because Q equals to D is a good choice because then we can make G is what? 1 minus D inverse A, and D inverse is just flip the diagonal elements, is just a one-time thing, and I can compute it again and again and again. So it's like a very nice in terms of computational costs. What else? I could choose my Q as the D plus L, where D was the lower diagonal. L was the elements below the diagonal and D was the diagonal. I could choose that. This is known as the Gauss Siedl method. And Gauss Siedl method converges for any starting points if A is a symmetric positive definite. This is just here. Yes, so next class, next slides. I'm at the end of here. I remember I want to do the derivation myself of the Gauss Siedl method. So let us take a break here. We do Gauss Siedl in the next video.